It's been 1 year of observations from the James Webb Space Telescope. And what a year. There has been so many interesting observations, discoveries, pictures of nebula, galaxies, clusters, images inside the solar system, newly forming planets, detecting fascinating chemicals in the atmospheres of planets around other worlds. And this is just the first year. Some of the observations were kind of what we were expecting to see, and others were complete surprises, things that are going to reverberate through cosmology for years to come. So with this episode, we're going to give you a comprehensive look back at what happened for the first year of observations with JWST. All of the great pictures, the interesting science results, the new discoveries, the things that make you scratch your head and go, what? And some of the problems that the telescope experienced and what the future holds for year 2. Now, if you were really excited about the launch of JWST, but then you didn't really catch too many of the big stories that broke over the course of the year, this is a chance for you to completely catch up. You'll be able to talk with your friends, understand all of the science that was made over the course of the year. And if you just want a reminder, if you want to just have some nostalgia about some of the amazing discoveries, the really cool pictures that we saw this year, this video is for you. So let's start with the pictures. The first picture that I want to look at, and this has got to be one of the best pictures taken all year, is of the Tarantula Nebula. And the Tarantula Nebula is one of the largest star-forming regions that astronomers have ever found. It's located in the Large Magellanic Cloud, which is a few 100,000 light years away from Earth. So it's not even inside our galaxy. It's in a completely separate galaxy, and yet it is so big. There are so many stars forming, many of which are dozens of times the mass of the sun. You're going to hear me say this a bunch of times, and that is that JWST is equipped with a range of infrared instruments. And infrared is this wavelength of light that allows you to see through the gas and dust that normally obscures places like star-forming regions. And so under the Hubble Space Telescope, you might just see this blob of dust. But with James Webb, you can peer through the dust and actually see the stars as they're forming inside these cocoons of nebula. And in this picture of the Tarantula Nebula, you can see all of these knots and regions where new stars are forming. You can see through the gas and dust to some of these protostars as they're blasting out radiation that is pushing away the nebula material and exposing the stars. And over time, these giant cavities of dust will just get bigger and bigger, revealing all of the stars. This is one of those pictures that you can go and dig up the full resolution image, and it measures 14,000 pixels by 8,000 pixels across. This was one of the first pictures that was taken by JWST. It's just that the astronomers decided to release the image of the Carina Nebula first and hold on to this one until later. While the Tarantula Nebula is probably the most significant star-forming region that we know of, the Orion Nebula is probably the most famous. And so it was inevitable that astronomers would turn JWST onto the Orion Nebula. And the Orion Nebula is a familiar object in the night sky. If you've got dark skies, you can actually see it in the sky with your own eyes, but you can definitely see it in binoculars or a small telescope. And so this picture is a region called the Orion Bar. And you can actually compare this image taken by Webb and the one that was taken by the Hubble Space Telescope. You can see these bright stars and how they line up. And then when you see that comparison, it really gives you a sense of how good the optics are on JWST versus the optics on Hubble. All of the major structures are there. It's just like they're in better focus. And that is the power of a 6.5 meter mirror compared to Hubble's 2.5 meter mirror. So one of the coolest pictures that came out this year is of a Wolf-Rayet star, WR140. Now, Wolf-Rayet stars, these are really newly forming stars. They're incredibly hot, putting out an enormous amount of radiation. And when astronomers looked at this original image of the star, they noticed these bizarre concentric rings. And this isn't like an artifact in the image. This is real. There are actually these rings in the nebula material around this star. So what's going on? The star has a binary companion. And so the star is blasting out this nebula material into this cloud around it, and then this stellar companion is moving through this material and carving out rings as it goes. And so you get this ring after ring after ring. It's kind of like measuring the tree rings to figure out how old a tree is. But in this case, you know that this binary companion flies past the star every 8 years. And so each one of these rings matches 8 years of time of stellar evolution for this young star. The most iconic picture taken by the Hubble Space Telescope has got to be the Pillars of Creation. This is another star-forming region. In this case, you're looking at the Eagle Nebula, which you can see in a small telescope. And in fact, with a small telescope, and if you've got a camera attached, you can actually take pictures of the Pillars of Creation. But nothing like this. And so I mentioned earlier on about the Tarantula Nebula, how these stars create these really powerful stellar winds. Well, these stellar winds can shape the structure of the nebula around it. And so the Pillars of Creation are these places where the very top of it, you've got this newly forming star that is surrounded by this envelope of gas and dust. But then the collective power of all of the other stars in the nebula are blasting away like wind, like sandblasting this material away. And it forms like a comet-like tail, a column leading away from the star. And astronomers think that in fact these pillars, as we see them today, have already collapsed due to the powerful stellar winds. It's just going to take us a few thousand years for us to see a newer version of it. And once again, with the original Hubble version, you got this wonderful picture, and then James Webb comes along and takes an even higher resolution picture that also sees through some of the gas and dust that's obscured by the Hubble Space Telescope. And so you see higher resolution, but you also have almost X-ray vision to be able to see into these star-forming regions. And James Webb is equipped with multiple instruments that are good at different things. So in the first picture, this was taken using NIRCam, the Near Infrared Astronomy camera. In this second picture, you're looking at the image using the mid-infrared instrument, or MIRI. And so it's a different wavelength of infrared light. And so with MIRI, you get all of the gas and dust that is surrounding the stars, but the stars themselves disappear because they're no longer covered in the gas and dust, and they just don't appear bright in this mid-infrared. And so different wavelengths of light as they come into Webb reveal different parts of the nebula. And of course, astronomers are able to use this to learn a lot more about what's going on in this star-forming region. James Webb has been turned on newly forming stars that aren't surrounded by clouds of gas and dust. And in this case, you're looking at a protostar. It's designated as a class 0 protostar. And so this means that the star is only about 100,000 years old, and it's located about 430 light years away from Earth. The star is surrounded by an accretion disk, this sort of disk of material that's being pulled into the star to add to its size. And it's in there where we would expect to see planets starting to form around the star. And then the magnetic field lines are whipping out this material along the poles of the star, blasting off into space. If you could go back in time and look at the sun as it was forming in the solar nebula, this is the kind of thing that you might see just a few 100,000 years after the solar system started to form. We got a lot of galaxies seen by James Webb, and when you see these pictures, they're instantly recognizable. I call this the eldritch horror version of astrophotography because the colors are these sort of dark purples and salmon color, and they sort of make you think about some kind of gothic horror. All right, huge props to Judy Schmidt, who's an imaging specialist, and she kind of pioneered a lot of the early work with the images coming from the James Webb Space Telescope. Before the astronomers and the visualization specialists working from space agencies and universities, Judy was in there looking at the data as it was coming off of the telescope and putting together images that we could see. And so the colors are very recognizable because the regions of a galaxy that light up in the infrared spectrum are once again these areas of gas and dust, less of the bright older stars and more of the regions where these stars are forming. And often stars form in the galactic arms of their galaxy. And so the images from James Webb really show off where the arms in the galaxy are, where the star formation is happening, where we can expect to see future star-forming regions. It's like the skeleton of a galaxy. Not only is James Webb a powerful telescope, but when it lines up with a gravitational lens, it becomes an incredibly powerful telescope, where you're using the gravity of an entire cluster of galaxies as a natural telescope lens. And with that, you can observe objects on the other side of the lens with more precision to see what kinds of elements are in these distant galaxies that you just wouldn't be able to see with the capability of the telescope itself. But you get some other advantages as well. And in this case, James Webb was able to see multiple versions of the same supernova going off in a galaxy because the light has to follow a different path around this gravitational lens, around this cluster. So astronomers were able to see a type 1a supernova go off in a galaxy that was lensed by a galaxy cluster. And they were able to see it go off multiple times, depending on the length of the journey that the light had to take to go around the galaxy. It's just amazing. Like, I know it's not a James Webb thing, but just the fact that you can use the gravity of a galaxy cluster as a natural telescope to be able to see objects tens of thousands of times better than you can with just your telescope alone. Like, we don't know what dark matter is, but we can use it as a telescope. This picture will look instantly recognizable as a James Webb picture because you see that six-sided star. And of course, that's coming from the hexagonal shape on the mirrors that give all of the bright objects in images from Webb this very distinct six-pointed star image. And in fact, if you look very closely, there's actually two additional lines that come from the struts that hold out the secondary mirror on James Webb. And this is an object known as ARP 220, which is two galaxies crashing into each other. And the resulting merger is so bright that it is starting to overwhelm the sensors on JWST to be able to show these images. We've seen this picture in visible light, and it's fine. You know, it's pretty cool to see two galaxies coming together. But because you've got all this gas and dust mashing together, it's incredibly bright in the infrared. It's shining with the light of 1 trillion suns, about 100 times brighter than the Milky Way would look. And this is the first step to the sort of long decline of the giant galaxies. Eventually, this will turn into one of these giant elliptical galaxies. Think about galaxies like M87. They are the result of all of these giant galactic collisions that have sucked up all of the smaller dwarf galaxies, the larger galaxies in their region. There's nothing left to eat, and then they just settle down, form this giant ball of stars, and fade away into redder and redder stars over time. The picture that NASA chose to celebrate the first year of James Webb observations was this picture called Rho Ophiuchus. And this is the Rho Ophiuchus star-forming region. It's only located less than 400 light years away from Earth, and it is the closest star-forming region to Earth. So we've had like the biggest, the best known, the one that was made iconic by Hubble, and now we've got the closest star-forming region. It's a very small star-forming region. There's only one star that is like the size of the sun or larger, and it's the one that dominates the lower left of this image, and the rest are smaller. They'll probably turn into red dwarfs over time. Thanks again to the infrared view, we can see through all of that gas and dust and to be able to see the star underneath. And one of the things I really love about Rho Ophiuchus, like this is an image, again, that you can take a picture of with a small telescope, or if you've got a digital camera and a good tripod during the summertime when the Milky Way is overhead, you can take a picture and see this incredible region just in the Milky Way. It's such a great object, very famous. All right. We've looked at all the pretty pictures. There's lots more pretty pictures to come, but let's really talk about the science. So let's look at the scientific capability that Webb was designed to fulfill. And this is to use its infrared instruments to look back to the beginning of the universe, the time when all of the building blocks of the modern galaxies that we see today, that they were all coming together. And this is because the universe has been expanding over time, and the light that's been coming from different objects has been redshifted. And so even though it may have started out in the ultraviolet or in the visible light spectrum, over the billions and billions of years of the expansion of the universe, the light has become more and more redshifted. Things that were in the visible light 13 billion years ago are into the infrared today. And so it requires an infrared instrument to be able to see that far back in time to that great distance. The big expectation was that James Webb would allow us to see the earliest galaxies ever seen, the ones as they looked just a few 100 million years after the Big Bang. And the Hubble Space Telescope had already taken our view back to, in some cases, really just about less than a billion years after the Big Bang. And so it was expected that James Webb, with its increased power and capability, could take that further. And it did. And within a few weeks of Webb coming online, we saw paper after paper with people claiming to have seen the farthest galaxy, the galaxy the earliest after the Big Bang. And we saw numbers that were 300 million years after the Big Bang, 200 million years after the Big Bang, maybe sooner. But then you got a whole series of other papers that were taking a really careful look at the research that was being done. So at this point, the consensus is that the galaxies are seen between 300 and 400 million years after the Big Bang. And the techniques have improved. And so now you can expect that every couple of months, we're going to see a slightly more distant galaxy. And this is because Webb is doing these enormous surveys of the distant galaxy. With the Hubble Space Telescope, we have the Deep Field Survey, where they stared at this seemingly empty spot in the sky, observed for hours and hours, days and days, and they were able to see that it was actually filled with hundreds of thousands of galaxies. Webb is doing the same thing, but Webb is vastly more powerful. Webb doesn't have to take breaks. Webb is doing a survey and should turn up millions of galaxies in a very tiny spot in the sky. And some of these are going to be farther and earlier than anyone has ever seen. And so anticipate over the coming years, we're just going to see this record get broken over and over again. Who knows where it's going to end? But the most distant objects will probably be seen using gravitational lensing, where you use that power of a foreground galaxy cluster to be able to observe some object that you wouldn't be able to reveal. And more importantly, with that gravitational lens, you're able to see the chemistry of this distant galaxy, be able to see what it's made out of. But what was more surprising was the size and the scale of the galaxy that were being seen. In some cases, Webb was seeing galaxies that were as massive or more massive than the Milky Way. And the Milky Way has been around for the entire age of the universe. It took billions of years to pull together all of the dwarf galaxies and assemble this large, mature spiral galaxy. And yet, Webb is seeing galaxies like the Milky Way early on in the universe. And so this is one of the first major controversies coming from James Webb, that the early galaxies were too big, too early, and that if the galaxies truly were as massive as we're seeing them, then some of the underlying assumptions in cosmology, some of the models for how the universe came together, were incorrect. But astronomers have had the time to look back through the models, to look at the observations, and they're, although exciting, they don't necessarily break the widely recognized models of how the universe formed. The ratios of dark matter to dark energy, how these smaller dwarf galaxies came together to form the larger structures. One of the most exciting surveys that JWST is doing is called the JADES survey. This is the JWST Advanced Deep Extragalactic Survey. And this is this Webb version of the Hubble Deep Field, where it's staring at this one region. And there have been many hours assigned to Webb over the course of that first observing year. Many more hours are planned for the next cycle, which we'll get to later on in the episode. But already, Webb is seeing 10 times as many galaxies in the same region of space, with 15 times the detail that the Hubble Space Telescope saw. One of the most important tools that astronomers use to understand the chemistry of stars is called spectroscopy. This is where they take the light of a distant object, a star, a planet, whatever, and they break it up into a rainbow. And then they're looking for very specific lines along this rainbow called absorption lines. And those absorption lines tell you the chemistry of what's in that star, what's in that galaxy. And one of the most surprising findings is that Webb detected the presence of organic molecules seen early on. Another example where astronomers had to use gravitational lensing to be able to see it. But they detected what are called polycyclic aromatic hydrocarbons. And this is a byproduct of combustion. If you have a fireplace, you know the soot in your chimney, that's the same stuff. And they're finding it in a galaxy that is billions of light years away, early on in the universe. And of course, this is really exciting because the earlier on we see organic molecules in the universe, these are the building blocks of life and could help explain how complex organisms like we have here on Earth might have formed in the universe. Not only do we see the most distant galaxies, but we see the most distant quasar. Quasar, of course, is a supermassive black hole that is actively feeding on material. So much material that it can outshine the rest of the galaxy. The most active time in the universe is known as cosmic noon, and this is a couple of billion years after the Big Bang, when the star-forming regions in these galaxies were actively forming new stars, planets, and the supermassive black holes at the hearts of these galaxies were siphoning in material from the galaxy around it and shining these bright quasar lights out into the universe. But once again, it looks like the universe was able to get into this activity a lot earlier than anyone was expecting. And so we saw this quasar called Sears 1019, and it only contains about 9 million times the mass of the sun, so like twice the mass of the supermassive black hole at the heart of the Milky Way. But we're seeing it just 570 million years after the Big Bang. And James Webb saw other supermassive black holes a few hundred million years later, but some of which had already gained 1 billion times the mass of the sun or more. And so once again, how did these black holes pull together so much material so quickly in the universe? When you zoom out in the universe, you see the cosmic web. This is the large-scale structure of the universe, where you have galaxies, galaxy clusters pulling together into these giant structures. Astronomers describe these walls and filaments with large voids in between as the mutual gravity of all of these galaxies pulling together, and it's opening up these giant spaces in between them. And yet, once again, with James Webb, we go right back to the earliest moments in the universe, and we see the initial stages of this large-scale structure starting to form. In this case, it's just a handful of galaxies, but there is a massive galaxy that's acting like an anchor, and it's using its gravity to pull in other smaller galaxies to a long, thin filament of galaxies that measures about 3 million light years long. And this is seen just 830 million years after the Big Bang. The other big job for James Webb is to observe planets, both newly forming planets as well as more mature planets around other stars. And this is possible thanks to the infrared capabilities of the telescope. It allows you to see through the gas and dust of a star-forming region, to be able to see the planets as they're forming around newly forming stars. It allows you to measure the chemicals in the atmosphere of a planet separate from the chemicals in the star that it goes around. In order to do this, astronomers will point James Webb at a star where we know that the planet is going to pass directly in front of the star from our perspective. And so it takes images of the star itself, and then as the planet is passing in front, you get the presence of the atmosphere of the world. And from that, astronomers are able to determine the chemical fingerprint of that atmosphere. One image, WASP-39b, is located about 700 light years away, and it's a hot Saturn, definitely not a habitable world. And yet Webb was able to pick up a clear, unambiguous signal of carbon dioxide in the atmosphere of the planet. This is the first time that carbon dioxide had ever been seen in another planet. It also detected water vapor, potassium, sodium, carbon monoxide, other chemicals in the atmosphere of this planet. In many cases, the first time these chemicals had ever been seen in the atmosphere of another planet. And the most exciting worlds that we're all waiting to see are the TRAPPIST-1 system. TRAPPIST-1 is a red dwarf star that's orbited by 7 Earth-sized worlds, several of which are in the habitable zone around this star. And so if there's like any place that we know of that could have life, this is probably going to be it. Webb is going through these worlds one by one, examining their atmospheres or lack thereof. And so far, we only had 2 planets analyzed during this first year. We got TRAPPIST-1b, which is kind of like a super Mercury. And not surprisingly, there was no atmosphere. But the second world, TRAPPIST-1c, is one that astronomers were quite excited about. They're hoping that this might be like a super Venus. Unfortunately, again, no atmosphere. So we've got 2 rocky, airless worlds orbiting. But there's still 5 more to go. The ones that are in the habitable zone come up next. And so stay tuned this year when we find out the thrilling conclusion to what's going on with the TRAPPIST-1 system. In the world of exoplanets, we often don't get pictures. We get like the spectra data. We find out what the chemistry of the planet is. We're able to know what its orbital period is, the radius of the planet, the mass of the planet, but you don't get a picture. But if the conditions are right and you've got the right telescope, then you can actually take a direct image of an exoplanet. And this has been done from the ground many times, but Webb was able to take its first direct image of an exoplanet. The planet, again, is not Earth-like. It has 9 times the mass of Jupiter and orbits an A-type star, which is a very young, hot star that is much more massive than the sun. It takes 630 years to orbit the star at 92 AU, which is way beyond the orbit of Pluto. But because the star is so bright, giving off so much light, the planet is so large, and it's also far enough away that Webb is able to distinguish between the star and its planet. It was able to give this picture. So here is a picture of an exoplanet taken by Webb. Webb was also able to confirm an exoplanet. Finding planets is a bit of a process. So some telescope will detect a candidate planet. They'll notice a dimming of a star as a planet might have passed in front. But then astronomers have to do follow-on observations to say, yes, indeed, there is a planet there. And so there was a candidate planet that was found by TESS, NASA's Transiting Exoplanet Survey Satellite, and follow-on observations were done with James Webb to confirm that, yes, indeed, there is a planet here. It was able to use its near-infrared spectrograph and confirm that the planet is there, watching 2 transits as it's passed in front of the star. We don't know much. The planet is Earth-sized, but we don't know if it has an atmosphere, so it could be another target in the future for Webb to come back again and try to characterize its atmosphere. And not just planets. Webb has been observing brown dwarfs, and these are considered failed stars, giant Jupiters, somewhere in between a red dwarf star and a giant planet. And because these planets are cool, they're the perfect object to be observed by Webb with its infrared instrument to detect the heat coming from the world. And so Webb looked at a triple brown dwarf system. And in one of them, Webb was able to detect the presence of silicate in the atmosphere, sand. They were also able to see methane, carbon dioxide, carbon monoxide, sodium, potassium, and even water vapor. So many of these chemicals have seen before, but Webb is so powerful that you get this unambiguous signal for the presence of these chemicals in the atmosphere of this star. Many of the planets found so far are known as hot Jupiters. These are stars with several times the mass of Jupiter that orbit incredibly close to their star. We know about them because they're relatively easy to find. They have a large gravitational influence on their star. They also can pass in front of the star and block a lot of the light. And so a lot of these have been found. We don't know how common they are, but they're sort of like the low-hanging fruit of exoplanetary research. But thanks to Webb, we're able to study how these planets behave as they go around their stars. And so one of the most famous of these is called WASP-18b. And we've known about it since 2009. It just takes 23 hours to orbit around its star. This is a classic hot Jupiter. It has 10 times the mass of Jupiter. Thanks to Webb, astronomers were able to make a temperature map of the atmosphere of the planet to see where it's hot and where it's relatively cooler. And they were able to learn that the planet is tidally locked to its star, so it only shows one face to the star, and one face is far away. And so the side that faces the star is incredibly hot, and the side that faces away is still incredibly hot, but less hot. The day side is 1,000 degrees hotter than the night side. And one of the big questions that astronomers had was, how well can these planets regulate their temperature? Will the cool side be able to redistribute heat from the hot side? In the case of WASP-18b, the answer is no. The heat is not well distributed from the day side to the night side. James Webb has also spent some of its time looking at targets that are close to home, located here within the solar system. And at this point, Webb has looked at all of the planets that it can inside the solar system. It's looked at Mars, it's looked at Jupiter, Saturn, Uranus, Neptune. It can't look at the Earth Venus or Mercury or the moon, because it uses this giant sun shield to keep its instruments protected from the heat of the sun and the glare of the Earth and the moon. And so Webb has looked at all of the planets that it can in this first year of observations. So let's just go through the worlds. First up, we have Mars. And this is an image of Mars seen in infrared thanks to James Webb. We got two different wavelengths of radiation here, 2.1 microns and 4.3 microns. And what's interesting about Mars is that it absorbs a lot of heat from the sun and then radiates it again at night. And different kinds of rock emit different kinds of radiation. And so under Webb's view, you're able to see different kinds of rock on the surface of Mars. This was quite challenging because Mars is relatively bright, pretty much at the very limits of what Webb can see and try to resolve any features. So astronomers had to take extremely short exposures of Mars and then build up an image, adding all of that data together. Next, we have Jupiter. And this image came out just a couple of days after the full release of images and data came from JWST when it first started up back in July. We got hints of the raw image, and then astroimagers like Judy Schmidt came along and cleaned up the image and got some just amazing pictures of planet Jupiter. You can see the atmospheric bands across the planet. You can see the great red spot. You can see the haze above the north and south poles of Jupiter. In the case of infrared, the bright colors are the places where the warmer temperatures and the higher altitudes. And so that's why when you look, you can see the great red spot is one of the brightest objects in infrared on the surface of Jupiter. Next is Saturn. And this image just came out a couple of weeks ago from when we're recording this episode. The atmosphere of Saturn contains molecules that absorb infrared radiation. And so it looks very dim and murky in this infrared view. But the rings are quite reflective and quite bright seen infrared. And then you can also see a bunch of the moons orbiting around Saturn. Next, we have Uranus. In the case of Uranus, we're able to see its rings face on. And the rings of Uranus are very different from the rings at Saturn. Unlike the rings of Saturn, which are made of ice, the rings of Uranus are made of dust. And with these observations, astronomers were able to work out that the rings are made of larger chunks that are up to about 20 meters across. You can also see several of the moons of Uranus in this image. We've really got to go back to Uranus. It's time for new images of this planet up close. And the last planet in this tour is Neptune. And once again, the rings of Neptune are quite dusty, and so they show up quite nicely in the image from JWST. And we haven't seen these rings since Voyager made its flyby in 1989. You can see features in the upper atmosphere of Neptune. You can see these storms and bands across the planet. You can see a lot of the moons just hovering around the rings around Neptune. And then you see Triton, which is this really bright star that's off to the side of the planet. And as with the Hubble Space Telescope, you can expect that we're going to see images of each of the planets that Webb is able to see every year. And that will allow astronomers to be able to track changes to the surface of these planets, see storms growing, see the effects of different seasons, how they change the nature of the atmosphere on these planets. Over time, we'll get a much better understanding of how these planets change from year to year. But not just planets, we got some images of some moons. And in this image, you're looking at Enceladus, which is this icy moon of Saturn, known for the geysers that are spraying water ice out into space. We've only seen images of the geysers from the Cassini spacecraft, which was orbiting around Saturn and its moons. But Webb is powerful enough to detect the presence of these geysers from this enormous distance. Astronomers measured the size of these plumes and found that they extend about 10,000 kilometers into space. And from what they can tell, they're throwing about 300 liters a second of water into space. That's enough to fill an Olympic swimming pool in a couple of hours. The hope was that Webb would be able to see some of the other molecules that were detected by Cassini, the presence of hydrogen gas in the plumes or various organic molecules. And so unfortunately, with this set of observations, Webb was unable to see it. But we'll see over time, with more observations year after year, we may get those more sensitive signals starting to come out of this data. We got images of Titan. taken by the James Webb Space Telescope. Titan is Saturn's largest moons, and a moon with a very thick atmosphere where it rains methane. There are methane lakes on the surface, mountains made of ice, and Titan seems to have organic molecules on its surface. Even though the Cassini spacecraft was at Saturn, it doesn't have the same kind of optics, same infrared capabilities that the James Webb Space Telescope does. And so these images coming from James Webb are able to see through the haze surrounding Titan and reveal some of the surface structures. You can see some of the northern region called the Kraken Mare. And so with continued observations from James Webb, we'll get a much better idea of the geologic features on the surface of Titan. And this is perfect because NASA is sending a nuclear-powered helicopter to the surface of Titan in the next decade. Now we'll know where to look. So when asteroids pass in front of stars, you get this perfect opportunity to learn more about the asteroid itself. And in this case, James Webb was able to participate in an occultation of the asteroid called Charlikov. And astronomers know that this asteroid has rings. As the asteroid passed in front of the star, Webb was able to make really accurate measurements of the rings, to watch the dips in brightness as each one of the rings passed in front of the star. And of course, last year we had the DART mission, the double asteroid redirection test, where a spacecraft was slammed into asteroid Dimorphos, which is a moon of Didymus. Astronomers around the world, space telescopes turned to watch the aftermath of this epic collision. And Webb was able to see this expanding cloud of debris coming from asteroid Dimorphos from this amazing impact. And afterwards, astronomers were able to measure exactly how much of a change in the orbital velocity of Dimorphos around the larger asteroid. It's been an incredible year of science observations, but Webb wasn't without its problems. And the first big problem was that the Space Telescope was hit by micrometeorites. And this was expected, that there were these tiny bits of dust in the solar system that were expected to crash into the mirror and start to slowly degrade the optics capability of the telescope. But in May, a fairly sizable piece of dust crashed into the telescope, causing a noticeable amount of damage. Still, the capabilities of the telescope are fine, well beyond the expectations of the astronomers going into this, but they're able to detect this damage. And in fact, based on this damage, the people working with James Webb decided to change the way the telescope makes its orbit. So before, it would turn in all directions that it was capable of seeing to be able to look at whatever targets it was going to. But based on this, they decided that they're going to try to do most of their observations downstream behind the telescope as it's going around in orbit. So before, if it turns upstream, then you get the added velocity of the telescope and the piece of dust that is crashing into it. And so now in this case, only the pieces of dust that will catch up to it in orbit will crash into it. They'll hit it with less velocity and will do less damage to the optics. We also had a problem with Webb's MIRI instrument, the mid-infrared instrument. Now, MIRI has 4 modes of observation, and one is called the medium resolution spectroscopy mode. And so engineers were detecting that there was like excessive friction coming from this mode of this instrument. And so they shut this instrument down to be able to use the rest of its modes, and then they were able to diagnose the problem and bring it back online. And so for a couple of weeks, astronomers weren't able to use that one mode of the MIRI instrument. There was also a problem with the near-infrared imager and slitless spectrograph. And this wasn't a problem with the instrument itself, but they were having a communications delay problem sending data to and from the instrument. This object is important because astronomers use it to study, say, the atmospheres of exoplanets, to understand the chemicals in distant galaxies. And so they had to bring this instrument offline, debug the problem with the communication delay, and then put it back online. But at the time that we're recording, every part of Webb is working perfectly. But this is natural. All missions have various issues that crop up, and scientists are able to work with the instruments, try to repair them, try to bring their various modes back online, debug the software, install patches and updates, and keep the telescope running. But there's no part of Webb that you should be concerned about. At this point, the telescope is working above and beyond the original expectations. It's producing amazing science that astronomers can be proud of. And hopefully, if everything works well, we should be able to learn more and more about the universe thanks to Webb for decades to come. So what's next? This wraps up 1 year of James Webb observations. And as you can see, it's been a very busy year. And this is just a fraction of all of the observations that Webb made. Many of the time on the telescope was awarded to individual astronomers who were writing up their research papers. But they have a 1 year of embargo for their data, but then that data is released to the public. And so anyone can look through this older data, make discoveries, and write their own papers based on what they found. And so that first year was a lot of this embargo data. You're going to see the ongoing continued discoveries made by Webb, and then you're also going to see scientists getting their hands on all of that data that was gathered in the first year. And so we're going to see much more science coming out in this next year and into the future. I'm still kind of torn about how the data release system works. Like, on the one hand, you've got this 1 year of embargoed information for the astronomers so that if they've requested time on the telescope, they can take the time to do a proper study of the data, be able to release their results into a peer-reviewed journal, have other astronomers look at it, be able to publish it, be able to take their time and do good science. But at the same time, other people aren't able to work on that data, and maybe they can make other discoveries as well. But if you just release it to everybody, then it's a race. And it might be that the person who does their first paper is the one who gets the most publicity, and it's not necessarily the best science. We saw a bit of that, right? With these discoveries of the first galaxy, you saw person after person saying, I've seen the farthest galaxy. No, I've seen the farthest galaxy. Took time for astronomers to really sit down and study the data and figure out what are the signals of the farthest galaxies. And so I wonder, does this embargo process help do good science, or does it slow down the science that could be done? Let me know what you think. All of the observations that were made last year were part of Cycle 1. This is all of the priorities made by the Space Telescope Science Institute. They're the people who manage the day-to-day operations of Webb and Hubble. They have the master schedule of where Webb is looking at what times. Just a couple of weeks ago, we got the announcement of Cycle 2. These are all of the observations that Webb is going to make for its second year of operations. And once again, there's a lot of really exciting targets that Webb is going to be looking at. And over the course of the upcoming year, we're going to be able to report on what it's found. So there you go. 1 year of observations from James Webb. Everything cool that we saw in just this first year. But the telescope was doing great, and it was launched with a very precise orbit that looks like it's going to make it last for a lot longer than astronomers ever expected. It was originally hoped that they would get at least 10 years of operation out of the telescope, and now based on how well their orbital insertion went, it looks like the telescope's going to be around for 20 plus years, maybe 25 years. So hopefully I'll get a chance to do this 25 more times, at least, as we learn more and more about the universe. Now, of course, this is just the tip of the iceberg of all of the work that we've done on the James Webb Space Telescope. I write a newsletter every week where I give you a high-level overview of all of the interesting stories that broke in across all of space astronomy this week. We cover all of these stories in Space Bites every week here on the channel, so you can learn a little bit more and see some cool pictures. We write full-length articles on the Universe Today website about each one of the stories, and I do interviews with many of the scientists who've made the discoveries that we're talking about here today. And so we'll have links to the show notes to many of the interviews that went along with this episode, the people behind some of the discoveries made with James Webb. I hope you enjoyed this special bonus, very long episode talking about all the great discoveries made by James Webb. And we couldn't do this without our patrons. And I'd like to give a special thanks to Joel Yancey, Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltan, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew Gross, and Josh Schultz, who support us at the Master of the Universe level. You can join our amazing club. Go to patreon.com/universe today. It's hard for me to pick what's my favorite for the year. I think it's actually that last image of the Rho Ophiuchus cluster. Mostly because I'm so familiar with that object, to sort of see the image coming from James Webb was really exciting for me. But I'd love to know what your favorite picture or story was this year. Just put a note down in the comments. Let me know what was your favorite research done by James Webb in that first year.